Okay, this should be a short video, but let's show you how the area problem goes. So in the area problem, we can also use limits to solve and find areas. So you saw in the tangent line problem, we used the limit process to get the slope of a line, and from the slope of that line we got the slope of the curve. So remember what I said if we took the limit. Remember I said if we took the limit of this as delta x approaches 0, it actually will give us the slope of the tangent line. Well, the area problem works a little bit the same way, but it allows us to find the area under curve. You see this red curve right here, f of x? And notice that I'm going to go from x equal a to x equal b. Now these slanted lines are just to show you what the shaded region is. So what I want to do is figure out a way to find the area between the x-axis and this curve as x goes from a to b. So in other words, I'm looking for the area of the shaded region. Well, one of the things that we can do is we can create these little subintervals. Like I can, break the interval from a to b up into subintervals, and then I can use those subintervals to create rectangles. And you'll notice here the height of the rectangle is the function. So here the height of the rectangle is the function. Here the height of the rectangle is the function. Well, if I added up the areas of all these rectangles, well, that would give me an approximate area of the region. But the problem is it's not going to give me an exact area, because I'm going to have this error here, and I'm going to have an error here, and I'm going to have an error here, an error here, and so forth. But if I actually increase the number of rectangles, then what that would do is that would decrease the error. So now I didn't do it all the way across, but notice here where I had 2 rectangles, I now have 4. And so what that does is that trims down some of the error here that I'm losing. And of course, if I doubled the number of rectangles that I have in here, in other words, double the number of intervals, then I would, reduce some of the error. Well, if I keep increasing the number of rectangles, I'll keep decreasing the number of if I increase the number of rectangles, I'll decrease the amount of error. So the more rectangles I get, the less error I'm going to get. So basically what's going to happen is ultimately we can let the number of intervals approach infinity. That's the same as allowing the number of rectangles to approach infinity, and that will force our error to actually approach 0. Thus it gives us the exact area of the region. And this is discussed in detail later in the course, but right now let me just give you just a small little insight to it. Let's say that we wanted to estimate the area of the curve f of x equal x squared using 4 rectangles, only from the interval 1 to 2. So here you can see I have the curve y equal x squared, and there's x equal 1, and there's x equal 2. So notice I've created 4 rectangles of equal width. And of course, if you create 4 rectangles going from 1 to 2, then that basically would give you one would stop at 1.25, the next one would stop at 1.5, the next one would stop at 1.75, and the last one would stop at 2. So if you look at each of these rectangles, well, the width of each rectangle is 1/4 of a unit, 0.25. Now the height of each rectangle is just whatever the y value is, which would be x squared. So notice here, the height of this first rectangle is whatever 1 squared is. So that height is 1 squared, its width is 0.25, so the area would simply be 0.25 times 1 squared. The next rectangle, notice it's going to occur at 1.25. So the height is going to be associated with 1.25. So plug 1.25 into the function to get your height, 1.25 squared, and then 0.25 is the width. And then the next one occurs at 1.5, so plug 1.5 in your function to get the height, and then 0.25 is the width. And then the last rectangle, its height is right here. It's going to be the function evaluated at 1.75, and its width is 0.25. Now I calculated this on the calculator, and I got, when I added all the areas of these 4 rectangles up, I got 1.96875. Now, if you do it with 8 rectangles, well, with 8 rectangles, you're going to have, each rectangle is going to have a width of 1/8 unit, or 0.125 units. So the first rectangle is going to be at 1, and then the next rectangle is going to start at 1.125, and then the next rectangle is going to start at 1.25, and then the next rectangle is going to start at 1.375, and the next one 1.5, and so on. So basically these are the values, the left endpoints of each of my rectangles. And so since I know that the area of each rectangle is going to be width times height, and I know the width is 0.125, then the area of the first rectangle would be 0.125 times 1 squared, the height. The area of the second rectangle would be 0.125 times its height, which would be 1.125 squared. The third rectangle, 0.125 times its height, which would be 1.25 squared, and so forth. So each of these calculations gives me the area of the 8 rectangles, and then I grabbed a calculator and I added them up, and I got the area to be a little over 2.1484 to 4 decimal places. Well, if you allow the number of rectangles to approach infinity, which basically allows the number of intervals to approach infinity, you actually will get the actual area. And it can actually be shown using techniques that we'll discuss later that the actual area is 2.333, or 2 1/3. So the actual area is 2 1/3 units. So all of the 4 major problems will be discussed during the course. But for now I just wanted to focus on those 2 problems, the tangent line problem and the area problem. And now we'll move on to the bulk of calculus.